Hello all. Today we will be learning the fundamental topic from principles of communication system, that is line coding. So let's start. Learning outcome from this will be you will be able to understand the concept of line coding, learn the characteristics of line coding, distinguish among different line coding techniques. So this is a sender end, this is an receiving end. This is indicating what a line coding is. Sender is transmitting the bits through the transmission medium in the form of binary bits 0, 1, 1, 1, 1, 0. At the receiving end, the same bits are decoded in the reverse, that is 0, 1, 1, 1, 1, 0. To effectively transfer the binary bits from the transmission medium, line coding techniques are used. So, line coding is the process of converting a sequence of binary digits, that is bits or digital data, into digital signal. Line coding is implemented for digital transmission of binary information. At the sending end, digital data are encoded into a digital signal, and at the receiving end, original digital data is recovered by decoding the digital signal. Data are encoded in a way that the timing information of the bit stream is maintained and the logic levels, that are zeros and ones, can be detected. Now, let's list out the line coding characteristics. So, first characteristics of the line coding is data rate. Second is signal rate or baud rate. Third is bandwidth. Fourth is DC component. Fifth is baseline rendering. Sixth, self-synchronization. Error detection. Noise immunity is very important to transfer the binary bits in the form of various line codes through a communication channel. Finally, implementation cost and complexity of the system. So these are the line coding characteristics. Let us see the classification of the line coding scheme. Line coding is classified into basically three types: unipolar, polar and bipolar. We'll see the difference in the forthcoming slides. Unipolar is again divided into two parts. First is RZ, second is NRZ. RZ stands for return to 0, NRZ stands for non-return to 0. Then polar line codings are again having three types: return to 0, non-return to 0 and biphase. Non-return to 0 polar line coding are having two types: NRZ level and NRZ I. We'll see that next. Then biphase is having two types: Manchester and differential Manchester. Bipolar line coding technique is having two types: AMI, called as alternate markup inversion, and speedo ternary. Both are reverse of each other. We will see this in the next slides. So first type of line coding is a unipolar, and it is having two types: return to 0 and non-return to 0. It is using two values of the voltage, that is 0 and plus 1. It is using only plus V volt, so that's why it is an unipolar line coding technique. Now unipolar NRZ, that is non-return to 0 line coding scheme. Let us understand that how it works. First we'll draw or we'll take the binary bits that are to be transmitted from the transmitting end to the receiving end, and for transmission of these bits unipolar non-return to 0 line coding scheme is used. So let us draw the bits diagram here. in the form of zeros and ones. So first two bits are 1 1, next bit is 0, then again 1 1, and this is 0 1 0, then last two are again 0 as nothing is mentioned. On the x axis this is time, so this is 1 1 0 1 0 1 0 1 0 0 bits we want to transfer from the transmitting end. Let us draw the propagation line to indicate the other parameters and the NRZ line coding. These bits having a time period of t seconds indicated here by t for each bit. So on the x-axis the time period is considered. On the y-axis the voltage level. So 1 is represented by +1 and 0 is represented by 0. Now the NRZ, so it is not returning to 0 in between the bits, so that is non-return to 0. So NRZ is represented by again 0 between 0 and V holds. So 1 is represented by 1, again 1 is represented by 1, while there is a 0 bit, it is returning to 0. It will remain the same value. Then again it is moving on to the next level, that is 1, that is the transition is happening whenever there is a 1 bit. Now again 0, so it is at the 0th level only, so this is remaining at the 0 level. Again 1 is coming, it is changing to plus. So this is what the representation of the non-return to 0 line coding. So it is not returning to 0, okay, and the bit timing t is remaining same for every bit. Okay. Now let's next see the unipolar RZ, that is return to 0 line coding. The previous non-return to 0 coding suffers from lack of synchronization, because if there are multiple non-zero bits, then there is difficulty in detecting which bit is transferred. So DC component and baseline wandering problem is there. To overcome these shortcomings, the return to 0 code was developed. Now let us see how to represent the return to 0 line coding. So this is again the same bit pattern we are considering for representation of return to 0. On the propagation line these are drawn. Okay. Again each bit is having a period of t seconds, that is time period t. It is using the voltage levels as 0 and 1. Now return to 0, so every bit, one bit, it is represented for t by 2, that is plus V volt, and it is returning to 0 for half of the time period. See, 1 is represented for t by 2 and then it is returning to the 0 level, which is the basic 0 level here. Again next one bit is represented for half of the time period, it is returned to 0. This one is also represented, this one is also represented. So all the 1 bits are represented for t by 2 seconds as plus V hold, and then it is returned to 0. That's why the name is given as return to 0 line coding. These propagation lines are shown here to understand that every 1 bit is returned to 0 for t by 2 period of time. So this is what is returned to 0. This is 0 level and 0. Rest of the values, that is zeros, are remaining at the same level, that is 0. So RZ signal pulse is only half the length of NRZ pulse. So it is using only half the pulse width. Okay. So unipolar RZ, that's why requires twice the bandwidth of the NRZ coding. So it is requiring more bandwidth. So the main advantage of this unipolar RZ is ease of generation since you implement a single power supply. It is using 0 and 1 volt. Non-zero DC component is there and no error detection capability. Hence, performance monitoring is not possible in case of this return to 0 line coding scheme. Next line coding scheme is the polar line coding scheme. This polar line coding scheme is again categorized into 3 types: return to 0, non-return to 0 and biphase. So in the return to 0 it is using these voltage levels plus V and minus V. In NRZ, it is again using plus V and minus V. Okay. It is passing through 0 here for return to 0. NRZ is having two types, non-return to 0 level and non-return to 0 inversion, biphase Manchester and differential Manchester. So this line coding method uses two voltage levels of opposite polarity and equal magnitude, plus V and minus V. That is one positive and another one is negative, to represent the two binary states, that is 0 and 1. Let us see it one by one. First, let us draw the bit pattern that we want to transfer it from the transmitting end, and then we'll represent it in the form of non-return to 0 L, that is NRZ L. So this is the bit pattern that we want to transfer from the transmitting end. Let's draw the propagation lines for it. So these are the propagation lines we have drawn. The time period for each bit is t seconds. Okay. On the x-axis there is a time period, and 0 to V volts that we have taken. Okay. Now it is using two levels. So this is plus V, this is minus V. Okay. So first is what? Non-return to 0 L. Okay. In this, first let's see how 1 is represented here. So 1 is represented with minus V voltage. Next one is represented again the same, that is minus V. Now whenever there is a appearance of 0 bit, the transition of the level occurs to plus V. So this 0 will be represented here by plus V volts. Next is 1, so it will return to again minus V. This will be at minus V. Again 0 is coming, so it is represented by plus V. Again 1, minus V volt. Again 0, plus V, 1 and plus V. So you can see that in NRZL, the voltage level determines the bit value. Binary 1 is represented by a negative voltage and binary 0 is represented by a positive voltage. This encoding scheme suffers from the issue of baseline wandering because it is transferring from minus V, plus V, minus V and plus V. Where this NRZL is used, so NRZ is L is used in the RS-232 serial port communication. Now let us move on to the NRZ invert type of line coding scheme. So first again draw the bit pattern that we want to transfer from transmitting end, and it will be using the line coding scheme as non-return to 0 invert. So this is the bit pattern. Let us draw the propagation lines to indicate here the time period for each bit will be t seconds, and on the y-axis here it is plus V voltage for the bit you want to transfer. So 1 is represented by plus V, 0 is represented by 0, and then we will represent here the non-return to 0 invert line coding scheme. Okay. So first 1, how it will be represented by minus V. Next one will be represented by plus V. So you can see that first one is represented by negative voltage. Next one will be represented by plus V voltage. So there is a inversion. That's why the name is non-return to 0 inversion. Okay, it is not return to 0, but it is inverting between plus V and minus V. Now next is what? 0th bit. So 0th bit will be at the same level at the previous one. So the transition will be occurring here only when there is a presence of 1 bit. So 0 is there, the level will be at the plus V voltage. Now this is again the next one, so it will be returning to minus V voltage. Now next is 0, so the level of the NRZI will be at minus V only. When there is again 1, this will be changing to plus V. This is remaining at plus V and it is returning to minus V for the next one. Okay, and it is returning to the same value at -1 only, because the next is 0. So transition or no transition in the voltage level determines the bit logic. So whenever in the transmitting end, okay, these bits are transferred, but it will be detecting the change in the 1. So whenever there is a 1, there is only a change in the level of the voltage. So a bit that is being transmitted is at logic 1. A transition from one voltage level to another takes place. So whenever there is a 1 only, there is a transition. If there is a 0, there is no transition. Means at the receiving end, the receiver will come to know that there is a change, means there is a 1 occurrence. When there is no change, means there is a 0 bit. So this type of bit patterns are detected then at the receiving end. So a bit transmitted bit at logic 0, there is no transition of voltage level. When bit 1 arrives, the signal level is inverted. This is a code used in compact disc, that is CD, USB, and on fiber based fast Ethernet at 100 mbits per seconds. Okay, so this is what non-return to 0 invert type of line coding scheme. Now let us move on to next, that is polar return to 0. So first we'll draw the bits that needs to be transmitted from the transmitting end. Same bit pattern we are considering here. Okay. Let's draw the propagation lines to show the time period and individual bits, okay, to be represented for the polar return to 0. T time period seconds for each bit. It is represented with 0 to volt. So 1 is represented by plus V. Okay. Now polar is using two voltage levels, so plus V and minus V, and it is returning to 0. So first one will be represented by this type of sign. This is plus Z. Next one will be also represented by the same, that is plus Z. This is again plus Z, and it is drawn here. Okay. 0 will be represented by this negative pulse here, that is minus V. Again plus V, minus V, plus V, minus V, plus V, and minus V. So 0 is represented by minus V pulse. This pulse will be represented for half the period, that is T by 2 period here only. This is for T by 2. This is also for T by 2 period. So plus 1 is plus T by 2 and minus 1 is represented for 0 bit, that is minus V volt is represented for 0 bit for the period of T by 2 seconds. With the increase in the number of transitions, the synchronization between the transmitter and receiver is good, leading to self-synchronization capability. So there is a increasing in number of transitions. So how the transitions are increased here? One is represented by plus V volt, but that is for half of the time period of the T, that is T by 2. Okay. Then next is again plus V return to 0. So for everyone it is returning to 0 for half of the pulse width, that is T by 2, and represented by plus V. So every time at the receiving end, whenever it is getting plus V volt for T by 2, it will be indicating that there is consecutive ones. Whenever there is a 0, it is returning to minus V volt for T by 2 period. Again for T by 2 period 1. So these are the consecutive transitions for every bit in polar return to 0, and it is taking alternatively plus V and minus V voltage level for the time period which is half of the pulse width. Okay. So there is a self synchronization facility in polar return to 0. Now there is no DC component and baseline wandering problem in this scheme. Major issue with this is the complexity in generating the codes which incur due to the use of 3 voltage levels. So it is using V0 minus V. So for T by 2 period it is returned to 0. Okay. Then for 0 again it is minus V, and again it is returned to 0. So every time it is returning to 0. So there are 3 voltage levels that are used for polar return to 0. That's why it is complex to generate this type of code. But keeping in mind the deficiencies of this code, these codes are now being replaced by efficient codes like Manchester and differential Manchester. So let's have the look of Manchester and differential Manchester codings. Now, biphase encoding techniques, okay, which comes under the polar line coding techniques, and these biphase encoding techniques are two. First is the Manchester, second is the differential Manchester. So to overcome the limitations of NRZ coding, biphase encoding techniques are used. Biphase, okay, so it is we know first limitation is it is complex because it is using three levels, plus V, minus V and 0. The most common biphase techniques are Manchester and differential Manchester coding. Such encoding techniques are phase encoded techniques. So let us say first of all the Manchester coding. So let us draw first of all the bit pattern that we are using, that is 1101, again 10, okay, then again 100. These are the bit patterns. Let us draw the propagation lines for each bit to show the time period and the Manchester coding below the same pulses. Okay, so this is the t seconds time period that we are using. This will be 0 to V volt. It is used for representation of the bit pattern that you are transmitting. So here in Manchester coding, the 1 is represented by plus Z, okay, or we can say a Z symbol, and 0 is represented by reverse S. Always remember 1 is represented by Z and 0 is represented by this symbol. This is 1 and this is 0. Now let us see how the Manchester coding will be represented here. So it is using plus V. Okay, only one voltage level is used here. Okay, previously it is using three voltage levels, that is plus V, minus V and 0. Now here 1 is represented by, you can see 1 is represented by here with plus Z symbol. So this is plus Z. Okay, next one is again represented by plus Z. In order to show the continuity, let us join these lines. So this is 1, next one. Now 0 is represented by reverse S. So 0 is represented by reverse S. Again 1 is represented by plus Z. This is again S plus Z. This is reverse S plus Z reverse S. So this is Manchester coding. So major disadvantage is the requirement of a higher bandwidth, which is almost twice of unipolar or polar NRZ. So this is the Manchester encoding and it is used in Ethernet based local area networks. Let us move on to next, that is differential line coding. So again the same bit patterns are used to show on the graphs. Draw the propagation lines. So these are the propagation lines and it is using the t seconds time period using a single voltage level 0 to V. This is the basic binary pattern that needs to be transferred from the transmitting end, and let's see how it will be represented in the differential line coding. So in differential line coding, 1 is represented by either plus Z or reverse Z. Similarly, 0 will be represented by either this plus pulse or this negative pulse. Let us see how we can represent these values here. So it is again using a single voltage level, that is V volts and 0 volt. Let us see how this 1 will be represented here. Okay. So 1 will be represented with plus Z. This is represented by plus Z. Next one. Now the signal level is at 0. Next is again 1. So let us use the second symbol, that is reverse Z is used to represent this. So at the receiving end, the receiver will decode it as this is plus Z, so this is 1. Again this is a reverse Z, this is 1. So this is how the detection capability in the differential line coding is there. Now next bit is 0. So 0 means currently the level of the signal is at plus V. So we will be using this type of pulse for the representation of 0. So this is what we are using here. Correct? Yes. So this is the 0. Now next is 1. So 1 is the signal level here is at plus V. So we will be using the Z symbol here. Okay. So this is represented. Now 0 is there. So the signal level is at 0. So it is at 0 means we will be using this to represent the 0 here. Okay. So this is what the positive pulse is used to represent the 0. Now again next 1. We will use the reverse Z here. Okay. So this will be reverse Z to used. Now you can see that at the receiving end, the receiver will encode is, it will be encoding the signal as this is having this pulse, so this will be 0. This is having reverse Z, this will be 1. So this type of detecting capability improves over there for every transition. Again 0 is there, so this is using the negative pulse to represent this value. Okay, this is at the V level. Okay, not at the 0, at the V level. So 1 will be represented by the plus Z symbol here. Again this is 0. 0 means we will be using this first type of symbol to represent this. So this is how the differential line coding is used. So as it is using differential levels, so that's why the name is differential line coding. So if there is a binary 1, there is no transition. This is binary 1, there is no transition. Okay. This is as it is. Binary 1, no transition. Binary 1. Whenever there is a binary 0, there is a transition. So binary 1 is having no transition, binary 0 is having the transition is indicated on the line code. So this is about the differential line coding scheme. Now the bipolar line coding, in that there are two types of line coding, AMI and speedo ternary. AMI stands for alternate markup inversion and speedo ternary is reverse of AMI. So bipolar line coding uses 3 voltage level signal, positive, negative and 0 to represent the logic states. Bipolar signals may be RZ or NRZ. The presence of alternating code in this encoding prevents the buildup of DC voltage in transmission lines. The existence of long sequence of zeros and ones produces no transition in the data stream and therefore the loss of synchronization arises in bipolar line coding techniques. No bit transition is used, hence lesser bandwidth is required for bipolar line coding techniques. So whenever there is need for use of less bandwidth, bipolar line coding techniques are used. The most common bipolar encoding techniques are alternate markup inversion and speedo ternary coding. Let us see one by one. So first is alternate mark inversion called as AMI. Let us draw the bit pattern that we want to transfer from the transmitting end through a communication channel. Draw the propagation lines to show the AMI signal and the time period for every bit. So T seconds we are considering here. So the voltage levels are 0 to V volt. Now let us draw the AMI line code. So it is using 3 bit levels plus V and minus V. Okay. Now plus 1 here, it is represented by plus 1 or plus V volt. Okay. Next one will be represented by minus V. First one plus V, next one minus V. Next is 0. So 0th will be, it will go to the 0 line, that is to the AC line here. Next is again 1. Now the previous one was at minus V hold. So this one will be going to the plus V hold. Okay. Now this is to the 0th hold. Next one will be minus V. This is 0. Then plus V and again 0. So here we can see that the consecutive ones are shifting from plus V to minus V. Whenever there is a 0, it is on the DC level. So binary 1 alternates between positive and negative voltage levels. So it is between alternate plus V and minus V. Okay. So in AMI, long runs of 0 produces no transition. So if there is no transition, the receiver will understand that there are continuous zeros are there in the transmitting line code. And whenever there is a transition, that is plus V minus V, then the receiver will conclude that there is a value as 1 bit. So there is a loss of synchronization, because if there is a long stream of 0 bits, the synchronization may get lost in this case. So AMI coding was used in first generation digital telephony PCM networks. Now let's see the pseudo ternary line coding, which is just reverse of the AMI line coding technique. The term pseudo ternary refers to the use of 3 encoded signal level to represent the two levels, that is the binary data 0 and 1. The alternating positive and negative pulses represents binary 0. First binary 0 is indicated by plus V and second binary 0 is by minus V. Pseudo ternary is the reverse of AMI. Okay. So let us see how we can represent the bit patterns here. So first, these are the bit patterns that we want to represent using the pseudo ternary line coding in order to transfer to the communication channel, and at the receiving end the bit pattern should be recovered. So these are the propagation lines. So these are all the propagation lines. Okay. This is the T time period 0 to V. Now it is using again the 3 voltage levels. So first one will be represented by 0. It is reverse of the AMI. In the AMI we are representing 0 at the 0 level. Here it is represented 1 at the 0th level. So 1 is represented on the 0 level. Next is 0. So first 0 is represented by plus V volt. Okay. Next is the 1. That's why it will be reaching to again 0 level. Next is again 0. This 1 will be here represented by plus V. So the consecutive one, next one 0 will be represented at minus V. Now this is 1, so it will be returning to 0 level. This is again 0. Now this 0 was represented as minus V hold, so this will be represented at plus V hold. 1 will be represented at 0. This is 0. Previous 0 was at plus V hold, so this 0 will be represented at minus V hold. So binary 0 alternates between positive and negative voltage levels. This is just reverse of the AMI logic. Okay. And 0 voltage for binary 1. So thank you. So here we have covered the various line coding techniques. I hope all of you are understood this, and if a code is given, you will be able to generate a respective line coding using the typical line coding scheme that we learn. Thank you.